In this video, we're going to do some more exam-style questions using the constant acceleration equations. In the first, we're told Anila is practicing catching tennis balls. She uses a mobile computer control machine which fires tennis balls vertically upwards from a height of 2.5 metres above the ground. Once it has fired a ball, the machine is programmed to move position rapidly to allow Anila time to get into a suitable position to catch a ball. The machine fires a ball at 24 metres per second vertically upwards, and Anila catches the ball just before it touches the ground. In part A, we're asked to draw a speed time graph of the motion of the ball from the time that it's fired by the machine to the instant before Anila catches it. Before I do that, I just want to sketch a quick model. So modelling now the tennis ball as a particle, what we're going to have is this scenario. So we're going to have now a height of 2.5 metres. So we're going to fire it, it's going to come up, it will then now hit a velocity of 0, it will come back down, and then she will catch it, and that will be now 2.5 metres below now the speed, the point of release. So what we'll have, let's put the value right there. So that is going to be 2.5. Now this doesn't have to be wildly accurate, it's just going to give you some idea of what's going on. So this right here is 2.5, so we've got 2.5 metres. So let's go ahead and draw our speed time graph. Now with the speed time graph, this isn't a velocity time graph, therefore we're going to have no negative portion of this graph. Speed is the absolute value. What I'll do as well is look at a velocity time graph based on this information right here. So this will be v meters per second, this will now be t seconds. So we're told now in the question that it's fired with a speed of 24 meters per second. So what I'm going to do is start this now here, and that's going to be 24. It's going to come down to 0. That's the point here. So when now the ball reaches its maximum height, the speed will be 0. Then it's going to come back up this way and end higher than where it started. So what we're going to have then is 24 just here, and then we're going to have some value, and we need to show that that's going to be higher. So if this was a velocity time graph, it would do something like so. And I would put now here that this was minus 24. So if I wanted to extend this, let's just extend this down. I would say now if this was a velocity time graph, I'd have this, and I would say now that this is going to be the point, and I'd make it quite clear that this was going to be minus 24, such that it could be shown that that is below. But this is what we need. We need this right here, the orange graph. In part B, we're asked to find to the nearest centimetre the maximum height which the ball reaches above the ground. So let's consider now this height right here. We're looking for this, which I'll call h, plus the 2.5. Often pupils leave out the 2.5 and just put h. This now is the distance above the ground. We're interested in this height. If we were asked for the height above the point of release, then that would just be h, but the height above the ground is 2.5. So let's collect some information using SUVAT. So we've got s, which is the displacement, we've got u, which is the initial velocity or the speed of release, v, the final velocity, or if you like, now essentially the speed at which she catches it, and then the acceleration and the time. I'm going to take up to be positive. If I take up to be positive, the acceleration will be minus g, or minus 9.8 meters per second squared. I've got u, which is the speed of release, which I'm given as 24. At this point here, v, the velocity, is going to be equal to 0. It's going to stop and then come back down. Therefore, I can say my final velocity is 0. I'm going to give now the displacement a value here. That's going to be h. So we want to solve for h. I've got 3 pieces of information. I need to find the fourth, so I can use v squared is equal to u squared plus 2as. So let's put this information in. 0 will be equal to 24 squared plus 2 lots of a, which is minus 9.8, and then multiplied by s, which is h. So let's solve for h. We've got 2 lots of 9.8, which is going to be 19.6 h. I'm just adding that to both sides, is equal to 24 squared. So h will be 24 squared divided by 19.6. So that's going straight for a calculator to find that value. Let's grab that up. So we've got 24 squared, and we're going to divide this by 19.6. That gives me now 1440 over 49. So let's write this here. So 1440 over 49. Now we need to add the 2.5. Therefore, the max height above the ground is 2.5 plus this. So we need to give this now to the nearest centimetre. So let's do that. So let's plus 2.5, and that's going to give me, what's that, 31.88 and so on and so forth. So to the nearest centimetre, 31.89. So 31 metres, 89 centimetres. And that's now to nearest centimetre. So that's what we've got, like so. We need to calculate the speed at which the ball is travelling when Anila catches it. Let's look at our model here. Now, it's projected from this point, and she catches it 2.5 metres below that point. So when we collect the information, we've got SUVAT. I can take, again, if I like, up to be the positive. If I do, now this displacement will be minus 2.5. It's landing now, or it's being caught 2.5 metres below its point of projection. Speed of projection 24. We've got now minus 9.8. So minus 9.8. I'm using this information. I'm not going to use the other information here. Now I could of course use that, but that assumes that I got this correct, because all I could do is work out now, if I started here, this distance, a speed now of 0, and then I would look at this height right here and work it out. I'm not going to do that. I'm going to use the information that they've given me. I call that clean data. So I know that my calculations are not including something that is potentially incorrect. So we want the speed. So again, using v squared is equal to u squared plus 2as. So v squared is equal to u squared plus 2as. I'm going to have now v, and remember we're taking the speed, so it'll be the positive root now of u squared, which is 24 squared, plus 2 lots of minus 9.8 multiplied by minus 2.5, which of course will give us a positive value when we multiply these two. So I want now the square root of 24 squared plus now 2 lots of 4, what have we got, of 9.8 times by 2.5. I'm going to leave the negatives off as they're going to essentially cancel, and that leaves me 25. So that works out quite nicely to be 25, and that's meters per second. So that is the speed right there. Okay, now, next part, in part D, we need to calculate the length of time that the ball is in the air. I could use all of this data. I could use this clean data. Alternatively, where's my clean data? My clean data is just here. Alternatively, I can use this information. Now, if I do this, I've got the choice. And I'm going to say now the following. I'm going to take down to be the positive. So taking down to be the positive, and you can take up to be the positive. I'll show you how it's done upwards as well. Let's consider what we've got. We've got 2.5, we've got minus 24, we've got 25, and now we've got 9.8. If we just look at this information right here, we can go ahead now and work with this. So I could work with the clean data. The clean data now is the 2.5, the minus 24, and the 9.8, because I've taken down to be positive. I didn't have to do that. I could have gone the other way. I could have taken up to be the positive. Up is going to be minus 2.5. We've got 24. Now the velocity would be minus 25. It's in the opposite direction, and the acceleration would be minus 9.8. So if I trust my information here, all I need to say then is v is equal to u plus at. Or if I wanted to do it here, I could take this one. We'll get exactly the same. This is taken down to be positive. This one is taken up to be positive. So v is equal to u plus at. So subbing this in, we've got 25 is equal to minus 24 plus now 9.8 t. Adding the 24, 49 is equal to 9.8 t. 9.8 goes into 49 exactly 5 times, so t is going to be 5. So it'd be 5 seconds. And you can see now that this is going to be exactly the same if we do it here. We've got minus 25. Minus 25 is equal to 24 minus 9.8t. And simply rearranging 9.8t is equal to 49. You can see the same. Now that's me using the value that I've found in a question. If I wasn't confident and if I had time, I could just use 3 pieces of information that I was given in the question. That is S, which is 2.5, assuming I'm taking down to be the positive. the acceleration, which is a given, and also the initial velocity. And you could have used now s is equal to, or in this one, if you're taken up to be the positive, s is equal to ut plus 1/2 at squared, and solve this quadratic. This is going to be far longer, but you're certain to use the correct information. So let's now take up to be the positive. Minus 2.5 is equal now to ut, which is 24t, and then we're going to have now minus 4.9t squared. So subbing in, that's what we'll have. We'll have a quadratic equation in t. Rearranging, 4.9t squared minus 24t minus 2.5 will be equal now to 0. So in a calculator we could work this out. Our a value is going to be 4.9, our b value is going to be minus 24, and our c value is going to be minus 2.5. Now in this case it's absolute overkill, but in some questions you'll need to use this particular formula. So in the calculator, using the quadratic equation, we've got minus b. So minus b is going to be 24, plus or minus the square root of b squared. So that's going to be 24 squared, minus 4 times by a, which is 4.9, times by c, which is negative 2.5, and let's put that in, 2.5, and then we're going to put all of that now over 2 lots of a, which is 9.8, and now we'll get a positive answer, and we can see that's 5. So that's stacked up. And of course, if you want to take the negative answer, in this case, let's see what we'd have. This should be a negative number, and then it is a negative number. Now, it won't always be the case. You'll have some questions where you're expected to find, now you'll have 2 positive values of t, t1 and t2, and you'll work out how far or how long it's above a particular part here. So how long it's 2 meters above the ground. And you'd simply now take t2 from t1, where they're both positive. But as you can see, this way, trusting the information that I found is a lot quicker. Okay, so that one's done. Let's have a look at another one. Whilst looking over the edge of a vertical cliff 122.5 metres in height, Jim dislodges a stone. The stone falls freely from rest towards the sea below. Ignoring the effects of air resistance, A, calculate the time it would take for the stone to reach the sea. B, find the speed with which the stone would hit the water. Okay, so let's again just model this up. So what we've got then is this, and we've got this cliff right here, and then we're going to have now straight below, we're going to have the sea. So we're going to have something that looks like this, and I'll just model this now. This is what we're going to have. It's dislodged. When it's dislodged, it means now that the initial velocity or the speed of release is 0. It's just fallen off. So what we've got then is 122.5. So 122.5 meters. So here he is. This is where we start. This is where we end. Now, in this particular case, I could take down to be the positive. So if we wanted to collect information, let's collect some information. We've got S, U, V, A and T. So this time I'm going to take down to be the positive. So this is going to be 122.5. Acceleration will be positive 9.8. If we consider the initial velocity was 0, we want to calculate the time. That's going to be what we're looking for, which is t. So if you've taken this now to be positive as up, you're just going to have these negative values, and you just go ahead and solve, and it will give you exactly the same. So what we're going to have then is the following. We need to find t. So we can use s is equal to ut plus 1/2 at squared. We've got the s, the u, and the a. So let's do that. S is equal to ut plus 1/2 at squared. So we're going to have 122.5 is equal now to ut. That's just 0. U is going to be 0. And then we're going to have plus 1/2 at squared. So that's going to be plus 4.9 t squared. So we can see that t will be the square root now of 122.5 over 4.9. And again, we're going to take the positive root as it's going to be a time. So in the calculator, let's do that. 122.5 divided now by 4.9, and we end up with 5. So again, t is 5. It's a bit of a coincidence, but t isn't always 5. So there we go, t is 5. We need to find the speed at which the stone would hit the water. So let's take this information again right here. We've got S, we've got U, we've got A, and we want V. So this time I'm going to use V squared is equal to U squared plus 2AS. So we're going to have v will be equal to the square root of u squared, which is 0, plus 2 lots of 1 to 2.5 multiplied by 9.8, and this can go straight through the calculator. So square root of 2 times by the 1 to 2.5 times by the 9.8, and then that will give me that speed. And that's going to be 49. So again, works out to be a nice value. So v is going to be 49 meters per second. And that now is the speed at which it hits now the water. So they've worked out to be quite nice values. And if you spot ahead, you can probably even see some of these are multiples of 4.9. Okay, next part. 2 seconds after the stone begins to fall, Jim throws a tennis ball downwards at the stone. The tennis ball's initial speed is u meters per second, and it hits the stone before they both reach the water. We need to find the minimum value of u. Okay, this is quite a tricky question looking at it. What we've got then, this is going to be coming down. Now this is going to be projected with a speed of u. Whilst this fell, this is now being essentially launched with now a speed of u meters per second. So what I'm going to do is write SUVAT. I'm going to use the information right here that it took now 5 seconds for the stone to hit the water. And I'm going to use that. I'm going to come back to this. Now, what we're looking at is the following. If we look at this information, we know, and I'm going to take down to be the positive. Let's take down to be the positive. That's 122.5. Now, we've got u just here. We're going to have the acceleration now of 9.8. That's downwards. Now this time is going to be t minus 2. Let's just consider this. If we think about this, if it's going to hit it, what we want then is it to hit at the last point. We want them to hit just as they're entering the water. So that time is going to essentially be 5. So what I'm going to do is sub this in. But first I'll just set it up. So what we're after is the minimum u. So using s is equal to ut plus 1/2 at squared, we can say 122.5 will be equal to u, and then we're going to have t minus 2, and then we're going to have now plus half, which is 4.9, now of t squared, which will be t minus 2 all squared. Now, what we can say then is the following. We can say we want on here, we want the minimum u. So what we can say then is min u is going to be the point, and it hits it right at the last moment. So it's really, if you imagine the tennis ball, and it seems that these tennis balls are quite popular. 5 seconds and tennis balls seem to work quite a lot for these questions. We want the slower speed, so it's just going to hit at the last time. So what we take then, for minimum u, we're going to say t is equal to 5. So let's go in and sub this. So just imagine that this one is dribbling down, it's falling off, and then the other one is coming down like so, and then all of a sudden, just as they're about to strike, they go. So what we've got then is 122.5 will be equal to, subbing in now the 5, that's going to give me 3u, and then we're going to have plus now, this is going to give me 4.9 multiplied by the 9. Okay, so all I've done is essentially put in here 3 squared is 9. So let's do some calculations. Let's do 122.5 minus now 4.9 times by 9, so 4.9 lots of 9, and then we'll divide that by 3, and that will give me u. So let's put that straight through a calculator. So what have we got? 122.5 minus now 4.9 times by the 9, and we'll now divide this by 3. So let's go ahead and divide that by 3. So that's going to give me now 392 over 15. So 392 over 15. Ideally, well, you can see that that's a minimum. It could be a lot quicker, and they could now collide a lot earlier. So 26.1. So 26.1, and that'll be meters per second. Okay, so that part's done. In part D, if you had taken air resistance into account in your calculations, what effect would this have had on your answer to part C? Explain your answer. Now with this, I mean the effects aren't going to be massive, but essentially what we can say, if there's air resistance, because now the speed of a tennis ball is greater, we would have to consider air resistance for the tennis ball. Also the surface area. I mean, it doesn't really give you much idea about now the size of a stone relative to the tennis ball, but we'd say the increased surface area would to some extent be affected by the air resistance. So you're looking at the speed and the surface area of the tennis ball. Some brief explanation along those lines would award you the 2 marks or 3 marks or whatever it's given you. So there we go, 2 exam style questions looking at the constant acceleration equations.